Assalamualaikum and hello to everyone. In this video lesson, we will continue with part 2 for chapter 3. In this video lesson, we will look at subtopic 3.8 and the objective for this subtopic is on the right. Now, in this subtopic, we will be introduced to a new property which is closely related to the second law of thermodynamics called entropy. In simpler terms, entropy can be defined as the quantitative measure of disorder for a system. Or in other words, if we want to calculate the loss in quality, we can do so by calculating the amount of entropy that has been generated. For a reversible or ideal process, which we have learned before this, the entropy will remain constant throughout the process. And that is why a reversible process is also called an isentropic process. However, for an irreversible or actual process, the entropy is always increasing. And as a result of this increase in entropy, less energy is available to do useful work. Now, when we look at subtopic 3.9 later, we will be answering questions involving ideal and actual processes. Therefore, to differentiate between ideal and actual processes, the subscript S will be used for ideal process and the subscript A will be used for actual process. On the right are the equations to relate between entropy and ideal and actual process. Be mindful of the equations inside the red box as we will be using it a lot in this chapter and also for chapters 4, 5 and 6. As you can see in the equation in the red box, only the terms at the exit, which is state 2 here, has the subscript S and A. Remember that for an ideal process, the entropy will remain constant, and for an actual process, the entropy will always be increasing. Now, before we look at questions involving ideal and actual processes, let's look at the first example on how to apply the second law of thermodynamics to steady flow devices for ideal process. In this example, we will look at the turbine. You can pause the video to read and understand the question properly. Now, from the question, we know that for state 1, the pressure is 12.5 megapascal and the temperature is 800 degrees Celsius. After an expansion process, the pressure is reduced to 600 kilopascal at the turbine exit, and also mentioned in the question is that the process is an isentropic process, meaning that entropy at state 1 is the same as entropy at state 2. Now, for step 1, please try to draw and label the schematic diagram for a turbine. For step 2, to find the specific work of the turbine, we will use the SFEE, and since the mass flow rate is not given, we will use the SFEE in lowercase letters. But before that, please write the conditions for the turbine from the question. Start with writing the general equation for SFEE and then cancel the terms based on the conditions. Write what is left and then rearrange to find for specific work output. Now, since this is an isentropic process, the specific work output and the exit state is denoted with the subscript S, which here means workout S and also specific enthalpy H2S. Since the exit is at state 2, for final temperature, we will find the temperature at state 2 and this temperature can also be called T2S. In other words, the ideal temperature for state 2. For step 3, start with state 1, and please remember to check for the phase first, which we can see here is in the superheated region. Therefore, by using table A6 at pressure 12.5 megapascal, 800 degrees Celsius, we will read for specific enthalpy H and specific entropy S. Now, we read the value for specific entropy S because this question involves an isentropic process. Therefore, the specific entropy here at state 1 is equal with the specific entropy at state 2 later. For state 2, using table A5 at pressure 600 kilopascal, we compare the value for specific entropy with Sg, which we can see here is greater, therefore the substance is still in the superheated region. Therefore, using table A6, we must use the interpolation technique to find for specific enthalpy at state 2, and we can also solve for final temperature here at state 2. Now, for the interpolation technique, at table A6, 0.6 megapascal, we locate where our value for specific entropy is, and then interpolate for H2S and T2S. For those who have forgotten the interpolation technique, this is the example. And as you can see, we have interpolated for the values for specific enthalpy and the temperature at state 2. Now, to illustrate the entropy effect, we can later sketch a new diagram at the end of the question. But for now, step 4, we substitute and solve for the specific work output. Okay, now let's illustrate the entropy effect using a new graph called the TS diagram. Okay, so we have here the TS axis. Okay, since the substance is water, we have here the saturation line, and don't forget the temperature line for both of the pressures. We can plot for state 1, which we found to be superheated. Now, for an isentropic process, since entropy is the same, we can draw a straight line to state 2, which here is still in the superheated region. And for an isentropic process, we will label it as 2S. If there is an actual process involved, then we can label a state for 2A. Now, remember, for an ideal process, the entropy will remain constant. And for an actual process, the entropy will always increase. Okay, now let's look at the second example for the second law application. This example involves a compressor. You can pause to read and understand the question properly. For step 1, please try to draw and label the schematic diagram for a compressor. For step 2, to find the power input or work input, we will use the SFEE, but first remember to write the conditions based on the question. Now, write the general equation first and then cancel the terms based on the conditions. Write what is left and then rearrange to find the work input. Since the substance is a gas, H here is replaced with CPT. And for this question, it is an isentropic process. Therefore, the temperature at state 2 here has the subscript S, and the work input calculated here is the ideal work input. For step 3, find the required properties at each state. For state 1, since there are no properties to find, we can always write them down and also remember to convert the temperature into Kelvin. And state 2, we here have to find the ideal temperature, T2S, therefore we must use the entropy relationship equation for gases. Since the question gives us the value for pressure and temperature, we will use the pressure-temperature relationship equation. Substituting the required values, we can calculate for the ideal temperature at state 2. Now, to illustrate the entropy effect, we can sketch the TS diagram. Since the substance is a gas, we do not have to worry about its phase. Therefore, we can just draw the pressure line for state 1 and state 2. Next, we can plot and label for state 1 at the low pressure line. Knowing that the process is an isentropic process, we can draw a straight line and then plot and label for state 2S at the high pressure line. If the question involves an actual process, we can draw the actual process line and label it as state 2A. For step 4, substitute and solve the question to find the ideal work input for the compressor. We have come to the end of this video lesson. We will continue for the next subtopic in another video lesson. Please refer to the original notes for exercises. If there are any questions, please do not hesitate to ask. Thank you for your attention and have a good day.